Like you said, I'm VP of Engineering at TidalScale. I'm a systems guy. I've become a big data guy. And this is not working. There we go. So we got started about 4 years ago. CEO, founder at the time, Ike Nassy, was the chief scientist at SAP. And they were seeing this problem themselves with their own systems and their own customers, that the volume of data, the variety of data, was constantly changing. And their customers were struggling to keep up. So the question was, SAP, help us keep up, right? And so they worked on how to handle this. They came up with SAP HANA, as some of you may have heard of this. It's an in-memory database. That's a solution. Why is that a solution? Why is in-memory one way of handling big data? It's fast, right? But what's the problem? There's a lot of it. There's a lot of big data. There's a lot of data you want to look at. How do you get it all into memory? That becomes difficult. And it's very important to have it in memory. Is that a laser? Yes, it is. So these are some key speeds here, right? For the kind of data I'm seeing our customers deal with, the kind of data we use in testing in our lab, cache is nice, but we're not talking about data that fits in cache. DRAM is our next best bet, 50 nanoseconds on average. How often does your data fit in DRAM? Anybody? Are you working on data sets that fit in DRAM on your systems? Good. You're in the right place. So what ends up happening is you're going out, if you're lucky, to flash, right? And we talk to the flash vendors. One of the biggest flash manufacturers in the world backs us. 150 microseconds is generous. Notice the scale change. Nanoseconds here, microseconds there. For those of you who aren't up on that, that's 1,000 times slower. We converted it to dollars just to make it super clear, right? Up at this speed, you're talking about 50 bucks. Down here, it's 150,000. It's a big difference. You might get your answer, but do you get the answer in the time needed? Right? We talk to medical labs. Somebody comes in with a brain injury. They need an answer the next day, not, if they're lucky, next week. Right? God forbid next month if that's you with the brain injury. All right? So getting the answer fast is really important. So let's talk about the current approaches. You can subsample, right? Gets the job done, gets your big data to fit, but it reduces accuracy. You can use an algorithm, maybe get smarter, some sort of probability function, right? Again, it reduces accuracy. If we're talking about brain surgery, those won't do, right? Maybe your problem, it's okay to be fuzzy, maybe it's okay to reduce your accuracy. But the people we're talking to, that's not okay. They want an accurate answer. Okay. You can shard. You've got Spark. You've got manual sharding. You've got all kinds of techniques. But now you have to do distributed computing. How many people here are doing distributed computing to get their answers? All right, I see one. Anybody else? All right, a few of you. Keep your hands up. Is it easy? Does it fail? Okay, all right. So again, it works. That's why we do it. But it's hard. And it feels to me, as someone who's a systems guy, that everybody has to solve the problem. There's not a lot of reuse, right? The distribute, am I too loud or too soft? Am I okay? People in the back? All right. I get excited. The Cubs won. I'm still high. I'm a Chicagoan. The last time they won, obviously I hadn't been born yet. Big deal, big deal. Also, my daughter scored a goal at soccer today at the State Cup, also a big deal. Anyway, let's move on. So this slide we're talking about, unfortunately, it's a little dramatic, but it's true. I'm talking about medical research, brain injury. Well, here's the Challenger disaster, right? Probably everybody here knows the answer to this slide. But what ended up happening here is they had a data problem. They weren't looking at enough of the data. Now, obviously, this would have fit in anybody's memory, right? Maybe it was a presentation problem. They didn't explain it well enough. Maybe it was a political problem. But the relationship of the data, when you have it all, is super clear. That's the point that we're trying to make with that slide. Same thing with sharding, right? Let's say you're working with a big box superstore. Maybe you've got a few thousand of these. You can't fit it all in memory. So you have to shard the departments. You have to shard by product. That gets you those shards that fit into memory. But can you see the relationships? Do you understand that the person buying hammers needs nails? Algorithmically, obviously we all know that. But does the algorithm, does the machine learning, does the random forest you're using to predict customer behavior, does that see the relationship when it's sharded? When those shards are between nodes and the relationship crosses nodes, probably it doesn't. All right? But what if you have a single huge server? All right? Maybe some of you have the budget for a supercomputer. Please don't lean against the light switches. We'll all fall asleep. Anybody here got a budget for a supercomputer? Great, you're definitely in the right room. Right? If you have it in the server and it all fits, your algorithm, whatever you're using, whether it's random forest, rather GLA, GLM, any of these different algorithms, whatever your favorites are, it becomes easier to discover the relationships with those algorithms. It becomes easier to explore the data, because in some cases you're able to explore the data in real time because it's all in RAM now. Okay? There's also this bit there, you got to have the recent data, right? So this is when we talk about the volume of data coming in, right? One of my colleagues here in the room, he's very familiar with Wall Street and the stock market. He talks about the stock market data coming in terabytes a day, right? Recent data is important, but sometimes you want to go back and look at this historical trend line. If you have all the data in memory, you can now do this. Right? You've got the best of both worlds. You can look at trends, you can look at 2 terabyte feeds, you can keep up with everything. All right. This is the bit about accuracy. Right? Again, if you're working with decision trees, let's just go through this. Decision tree models, the error rates decline with data set size and tree depth. If I can have more data, and I can calculate against a bigger depth, right? That's what we're talking about here down on the bottom to the right. More depth, more data, 50 million observations here, the red line. I get more and more accurate. Problem with this is it chews up data, right? To do this right, to do this with your full data set, you're talking about many terabytes. Right, much more than a conventional server can hold. So this is the question we pose. If you heard it at the keynote, I'll repeat it a little bit here. What if servers were software defined? Now maybe you don't know the size of your problem. I was recently doing some work doing analytics, working on an analytics problem, years worth of stock ticker data. Question came up, how big is it? How much RAM do we need? So I booted a 6 terabyte system and found out it was 3.2 terabytes. Now I can boot a 4 terabyte system and know it fits. What am I talking about here? Am I talking about different big computers? No. I'm talking about a computer that I can scale to the size of the problem. If you don't know the size, that's okay. Start big. Start 20 terabytes. That's fine. Figure out the size of your problem, optimize for your problem. The computer, it's just software, right? Like software-defined networking, this is a software-defined server, right? The advantage here is you get it all in memory. You get the scale you need. Obviously, well, maybe it's not obvious. So if you think about this rack, right, these individual servers, maybe that's 256 gigabytes, maybe it's as much as 768, even more, but it's going to come with its own set of cores. Maybe it's 24 cores, maybe it's 48. With TidalScale, as you put those together, you get those cores too. You get the memory and you get the cores. You get the I/O bandwidth as well, right, for getting the data in and out. Right? So that means you have the size of the computer to the problem. That's what we mean by a software scaled server, right? Any questions? Okay. That's our story. Now, I'm the VP of Engineering. He just said that. I'm a systems guy. I've been doing Unix kernel work, been working with technology called virtualization now for almost a decade, maybe more than a decade. Scary to think about that. It's actually a fairly mature, very mature technology at this point. It was new when I was working with it. This is what we're talking about: VMware, KVM, Xen, Beehive, Hyper-V. These are virtualization hypervisor technologies. And Intel did a lot of the hard work here after VMware started the ball rolling so that you can just, many of you may be using this technology if you want Linux on your laptop or you're doing virtual desktop infrastructure at your employers. And you may know this already. You can just run whatever you want on a hypervisor and you don't have to change it. It just works. Okay? But what if you looked at that differently? Let me, if I can, I'll go back. So you see what's happening here? One server, many virtual machines. So that's the idea of VMware, Xen, KVM. It splits the system up into many little VMs. We don't want smaller computers here. We want bigger computers. So what is TidalScale doing? We're taking lots of hardware, putting what we call our hyperkernel. Think of it as a distributed hypervisor. So distributed computing is still at play here. This is still scale out. We're just hiding it for you. Not hiding it from you, hiding it for you. Right? So the difficulties of distributed computing are hidden. We manage that problem. What we present is a single virtual machine that spans that hardware, a big virtual machine in this case. All right? Same story. We're a hypervisor. The software you're running today, whether it's R, Python, MATLAB, AnyLogic, I can't name them all. They all just work. And they all work without changes. So the code you've written today to run on your laptop that runs on a big server today runs on a TidalScale server. You don't have to change it. Unless you want to use more threads because we have more processors, or in case maybe you have a hard-coded limit. We've run into that. Somebody had a limit of 200 gig. They never thought they would need more than 200 gig. Guess what? Now they have 20 terabytes. They need to change that constant. All right. So that software-defined server runs in the middle. You have your operating system, your favorite application. It all just works. And part of the reason I can say I've learned a lot about data science, Brain Trust is in the back here today, keeping me honest, is that we've got this machine learning layer ourselves, right? This is a big data problem that we have to solve for you, right? And we look at what's going on in the system, and we have virtual RAM, and we have virtual processors, and they move around back and forth to optimize the throughput of the problem. So if you saw the talk or you had a chance to grab a R white paper or something, the reason we're getting the results we get at scale is we're able to optimize the throughput of the job, right? Your analytics job in this case, by moving things around, by moving the resources around. So like I said before, everything just works. We got AnyLogic, we got KX, we got Spark. All of these tools you're used to using run on TidalScale. Now in the case of Spark, most of the time you boot a 4 or 10 terabyte system, you just run it in single server mode. But there are limits to our technology. Maybe you need hundreds of terabytes. Maybe you want a petabyte in memory. So Spark and these other solutions still have a place. They run on top of TidalScale. The nodes in that, the worker nodes are now, 10 terabyte nodes, and you need 10 of them to get your 100 terabyte problem in memory, but that's fine. It's a lot easier to have a 10 node cluster than a 1,000 node cluster, trust me. Right? If some of you have been doing works with clusters already, you know this. Going from 10 nodes to 100 nodes, really hard. Going to 1,000 nodes, you're now writing papers on computer science. Okay? All right. So we do this all the time. Personally, I do this. We do these benchmarks. Right? The whole point here is to do these things much, much faster than you could do them today. Otherwise, there's no value. In our solution, there's no value to the patient with a brain injury. There's no value to the stockbroker trying to place some bets on the market. So this was a test, TPCH power test. If you're not familiar with it, that's okay. It's just one of these standard tests out there for server performance. You can run on an EC2 on a 3.8x large system, decent size. You get out to about 500 gig, that's your best. After that, doesn't work. It takes too long. You don't have the patience for it, trust me. So what happens? You run it on TidalScale instead. The key here is you just scale out underneath the hood, right? As you need more memory, you just scale it out like it's a cluster. You run our software, it makes it one big computer. Your favorite database, your favorite SQL engine still just runs. You don't have to rewrite your application. Okay? And you get, in the case of this type of test, pretty close to linear performance. You're all data people, so I won't say it's perfectly linear, but it's close in this case. Okay? Oh, wrong question. All right. Now we did the same thing with open source R. Anybody here using open source R? All right. How about RStudio from now Microsoft? Yep. Anybody using Tibco Tear? No? No Tibco Tear? Okay. So in this case, we put together really sort of our own benchmark. We couldn't find one that had enough variety. So we took the CMS public data set. Many of you may be familiar with this. This is available to all of us to explore, to look for patterns, to try to analyze what's going on with healthcare. It scales from 32 to 680 gigabytes. It's a public, already scrubbed data set if you're not familiar with it. And we run load join, GAM, GLM, decision tree, random forest, and k nearest neighbors as we scale it out. All right? In this case, we ran it on a typical 128 gig server. Obviously, you could get more than that today. That's really not the point. The point is no matter what server you buy today, your data set will exceed it. But with TidalScale, you can just keep growing the server, right? 5 nodes works today. Next year you've got some more data, or maybe next week you have some more data, you add some servers, it's bigger. You keep going. And that line goes out further, if you've got the data to drive it. All right. So we've gone ahead and we've done work with Spark and Python and open source R. I'm going to go through that to some degree right here. So starting with Spark, you set up your Spark cluster, right? People raise their hands. Specifically, I know a few of you raised your hand about distributed computing. Are Spark cluster people here? Okay. So you're on the hook. Keep me honest. Okay? So, how do you get it right? Right? How do you size the JVMs? How do you know how many JVMs you need, how many workers you need? Is this a 3-day problem to set it up? Is it a 10-day problem? Do you keep having problems, sir? Does it just work? You forget about it?
Depends on the scale, how much data you're working with.
So sometimes not, right? So you can build and run your random forests, using Spark. If this is gibberish to you, that's okay. It's pretty much gibberish to me too. But you can do it. We did it. But you run into some what we call weird problems, right? Memory issues. Too many small files can be a problem because of, I think it's HFS underneath, doesn't like a lot of small files. Do you choose Python? You have to go to Scala. Spark streaming's not resilient. What we're talking about there is if you have flow problems getting the data into your cluster, it doesn't fail gracefully, right? And sometimes things don't work, and it's got nothing to do with you or your job, but you have so many pieces underneath. You've got Java, you've got Apache, and or the OS. If you're hitting some problem in any of these layers underneath, it just stops working, often with a pretty unusual error message. So it turns out, it's not enough to be a data scientist. You have to be a data scientist with help, or you have to learn a lot about IT to do it yourself. Yes? Did I get it right? Okay, thank you. All right, so let's go on. Python, I think, is next. Yes. All right, a lot easier, right? Just run out a single node. No biggie. Now, what if you have to go to a cluster? Same problem, but different, right? I feel like I'm repeating myself, but I think my point is clusters make things hard. Distributed computing is not a solved problem, and you can do it, but it's hard. All right? Now, open source R, what happens? Is there a distributed solution to open source R? Not at all. You can do some R analytics in Spark, but very little. Right? If you've actually looked at the libraries that run on Spark, it's a pretty limited set. I'm told it's not enough for most of you to get your jobs done. All right? But again, you can do it. I'm not saying you can't. What I'm talking about is the alternative. Right? What if you could just have a big server? So you just take that workload, you take the code you've written, you just start exploring it. You just start doing your analytics. No new tools, it just works. Okay? Any questions so far? Go ahead.
So how do you handle redundancy? Like if you have all these different servers running one down or whatever, do you accommodate that?
So the question is, how does TidalScale handle redundancy? So there's two answers to that question, right? So one is, well, there's probably three. Depending on your job and your job length, you don't need to worry about it, right? Because your odds of a failure. Remember, we're now running the job in hours or days that normally would take months. So the failure rate that you're worried about actually tends not to occur in the run length of the job that runs on TidalScale. That's one way to answer the question. In a true mission critical deployment, you would do the same thing with TidalScale that you do any, if your guest is Red Hat, Linux instance, you would run n+1 nodes and load balance across them. So this were some giant, maybe Walmart's here in the room, I don't know, and this is your e-commerce site, and it's mission critical that you're doing real-time analytics on your customers, then you'll have 2 or 3 or 4 TidalScales sucking in the feeds. So that way, if you have a failure at any layer, you have redundancy and through load balancing fail over to the other TidalScale. Now, we also have some very clever work that we'll be talking about next year. Next year is not that far away, about how we handle resiliency in our own cluster, right? If you go back to that big rack, if you had some spare nodes in that rack, when a node starts to fail, we can do something about it. Not in what we're shipping today, but what we'll be talking about next year. We're going to have that kind of ability to just keep running, right? Any other? Yes, go ahead, sir.
Are there any issues with multi-tenancy?
The question is, are there any issues of multi-tenancy? No.
What kind of barriers?
We recommend compartments. So you run Linux containers, and that's your tenant barrier. Okay? Go ahead, sir.
We imagine that you're running a job in which you estimated your capacity.
Right.
So I have a lot more capacity than I need for this particular job. And if there's some node, let's say, that's multi-scale, why would we not just automatically use the additional capacity?
Do you want to work with our architect? That's a very good point. So we have, that's actually on the drawing board. I just don't want to talk about what we're not, we're not shipping that capability today, right? But if you come back in a few months, we'll have a different story for you. But I want to be clear, it turns out these are not the common failures, right? That memory and CPUs tend not to fail. What fails is software. And the best way to deal with software failure is at the software resiliency layer. Yes, sir, in the back.
So in your cluster, are all those nodes the same type, or are they homogeneous or independent? That's one question. The
Yes.
other question is, do users have a choice to choose what kind of strengths and the capacity of those nodes?
So the question was, do these servers that we're running in the cluster, do they need to be homogeneous, or do the users have choices? I just want to make sure I don't have anything more to cover here. So I'll answer that question. I'll make sure I finish. So right now, today, we recommend homogeneous. That's going to be your better performing, most reliable setup. They're the same. But you can choose. So, I recommend 2P. Do people know what I mean by that? So the motherboard has sockets, and the common internet server has 2 sockets, and that's actually your lowest cost, highest performing, most reliable motherboard. Right? Some of you may be using 4-way, called 4P, or even larger systems, because that's how you get more memory in one box. Those systems actually fail more. Okay, so it's best to use these commodity 2P systems, same systems, Facebook, Amazon, Google. Those are the most reliable ones to buy. Those are the best to use for TidalScale. But it's an open question, and you may know better, do you want faster processors or more cores? Right?
So
Yeah.
your approach, what is the difference between your approach and those web scale company approach? Facebook and Google, they also have unified data cluster. They treat it as same. And also, there are other companies like SpringPass and Nutanix. What is your approach and their approach? I'm just curious. What difference?
So I'm going to go back to what I was calling the software scaled server. So so you're asking what's the difference between web scale, Nutanix, these other solutions. So those are data center sized, right? You use some sort of job scheduling program to run on a given server or given compartment on a server. But the problem or the difference is those systems are still limited by the size of the server or compartment they can run it on. What TidalScale gives you is a server that can be much bigger than any of those, what used to be those individual computers in your data center. So those guys might say they've got these many systems, these many cores, but when you go to run your job that needs 5 terabytes in memory, they actually don't have a system that can fit 5 terabytes. Okay? With TidalScale, you would. All right? And with TidalScale, you can do that without changing your tool, without learning about distributed computing, without learning about Mesosphere and job scheduling in Mesosphere. So for example, if you wanted this today, you could go to our website, you could reach out to us, you could go to our partner IBM, and you could run a 15 terabyte, 30 terabyte, whatever size you need in their data center. right? Or you can run it in your own data center. Software-defined servers make it easier, right, to run big data problems, memory-intensive problems at speed, right? Hundreds of times faster than, you know, NVMe over Fabric, SSDs. You have alternatives. I'm not saying you don't, but if you need an answer today or tomorrow or this week, depending on the size of your problem, this is a better way to go. RAM is always faster. Gordon Bell, one of the early believers, early pioneers in computing, industry legend, also the first outside investor in our company. So it's a new kind of computer that we've built using software, but it's available to you to run your software. Thank you. All right, more questions. Thank you. Go ahead.
So are my applications running in RAM or RAM core mixture that is determined by?
Yeah, I mean, it's running in RAM. Obviously, it'll get cached by local processors depending on where they are in a TidalScale server. So some of it will get cached and run at that super fast speed, but most people, when I look at the problems they're running, it's just so big, it blows the cache all the time,
So,
right?
So if I'm a customer that typically requires my computational fluid dynamics to run in a GPU, how is that addressed?
GPUs, we don't have a good solution for GPUs today in our product. That's something we're looking at. I guess the question I would ask is, if it doesn't fit in a memory, is it only solvable in a GPU, or is there an alternative algorithm? So I've talked to people where they go, oh, I didn't have that kind of memory, so I had to do a different solution. So we were doing some work with a large genomics analytics organization, and they had, the first algorithm they gave us was meant to be very low, small memory footprint. They had optimized to use, you know, the memory they had, and it wasn't a good algorithm on TidalScale because we had all this memory. And we said, well, we've got all this memory. Do you have a different algorithm? And they went, oh yeah, we had this other algorithm we gave up because we couldn't get a computer that it fit in. Right, so I would have to ask, you know, you're using a GPU because that's the right tool in your toolbox. Here's another tool. If it fit in memory, would you use a different algorithm? Maybe not. All right. But keep talking to us. We'll have a GPU solution as well. Okay? Go ahead, sir.
Hypervisor?
Well, you can, but marketing likes to call it a hyperkernel. So stick with hyperkernel for my sake.
So when you charge it, do you have a license?
Yes, we charge, I think the easiest way to describe it is we charge $1 a gigabyte a month, right? If you get it from like IBM. If you're buying a license from us, we usually do a 1 year, 3 year. So think of that as $12 a gigabyte a year, right? Okay.
How big can your customer go? How big can your customer go in terms of number of nodes?
So I've only booted up to 20 nodes, 15 terabytes. But then I haven't finished. But the software does not have that limit. The software will go to 50, 60, more nodes. It should go to 200, 256 terabytes. That's not, the limit is, my limit is my budget today. I haven't been able to buy a big enough cluster.
You can go forever.
Not forever, not forever.
Design constraint, right? It should be within a rack or what is the...
Say that again, it should be a design constraint?
Is there a, besides...
Oh, in a rack.
Yeah, is that...
So the question is that a design constraint that it needs to be in a rack? No. I would keep the racks adjacent. I haven't gotten into all the magic we do, but the magic, one of the things we do is we basically extend the idea of the motherboard across the rack. And the way we do that is with 10 gigabit networking. All right? Obviously 10 gigabit used to be cutting edge, now we're talking 40 and 100. That's fine, you know, can run faster if you need to. We optimize for 10. At a certain distance, believe it or not, you know, 10 gigabit, the latency gets up, right? You don't want to go across town with it. But if you're in 2, 3, 4 adjacent racks, you're fine. Yes, sir.
Understand how you charge work. This is an example.
Say that. I didn't hear the first part. Go ahead.
I'm just trying to understand how this would internally be working. So as a hypothetical example, let's say that I'm doing a program in Python or R, it's 100 gigabytes, I have 10 machines, 10, 20 gigabytes each, and I do something like group by data and then reduce it.
Mm-hmm.
How would the system know, okay, so internally, the software thing is running a single processor, and it has to have all this data in this one processor. How would it actually work to split the data up and do it?
Well, the simple answer, which maybe is so the question is, how does this actually work? How do we know? Right, really you're asking about our machine learning algorithm, right? So the question is, how does TidalScale figure out where to put the memory? How does TidalScale figure out where to put the thread of the processor, right? So, what I would say is you would run your Python in multi-thread mode. Don't run it as a single thread. Run it as 16, 32, some number of threads. And then as those threads execute, we do something called working set analysis. Now, if you're a computer scientist, you know what I'm talking about. This guy named Denning did the first sort of groundbreaking work on locality analysis back in the 70s, if you can imagine computing in the 70s, where the problem there was they had, at most, 32 megabytes of RAM. That was like a huge computer back then. But they had hard drives, hard drives the size of your washing machine, right? And again, the same problem. Hard drives were slow. RAM was fast. How do we know which bit of the hard drive should be in RAM? He came up with this algorithm around something called LRU, least recently used. LRU, Mark, I'm having a blank. Least recently used. And the least recently used stuff was the stuff you didn't need next. So that would get flushed out, and the new stuff would come in. That's what we're doing. While your Python is executing, microsecond by microsecond, we're actually looking at that execution stream. What's it touched lately? Not necessarily knowing what it's going to touch next, but knowing what it hasn't touched for a while. And the stuff that hasn't been touched for a while is over there. The stuff it's touching right now, the thread of the processing, your thread in Python, that CPU, is adjacent to the memory that it's currently using. And as that changes, we move the CPU around. I know that sounds funny, but we're in the world of hypervisors now. The processor is virtual. You can actually move the processor around. On our system, it takes about, I'll be generous and say 200 microseconds. We're probably doing it faster than that a lot of the time. But let's say it takes 200 microseconds. We had that in the chart, actually, at one point. So we move the processor to where the memory is, and now it's next to the memory. That's how that works. And there's that machine learning polynomial underneath doing the hard work. The really hard work is done by Cleone figuring out how to train it. But all right. Anything else? Go ahead.
Adding on to this question,
Yeah.
Is that machine learning piece that you guys are running, is that supplanting a cluster manager like Spark Standalone or Mesos?
It's
Working on top of it.
for the purpose of the TidalScale software scale computer, we're supplanting it. Right? You could still have Mesosphere with lots of TidalScales. Right? Think of us as another kind of hardware, right? We're just a server, but it's a dynamic, flexible, very big server. But it's still just a server to a Mesosphere. We're just a big server. Yes, sir.
But even, I understand that's quite impressive. But even a huge server, it's still a sort of capacity limit in terms of memory and disk.
Yeah.
How about it's approaching the limit? What do you do?
Then you run scale out on top of TidalScale.
Then,
So let's say,
It will take some time, because of latency. You have to wait, The data gonna redistribute, it's called a balance difference.
so the question is,
Unfortunately, of course, it's huge, right?
yeah, so let's say you're out at 100 plus nodes and 200 terabytes, and our service people say that's it for now, right? If you need 500 terabytes or 2 or 3 petabytes in memory, then you still have to do a Spark cluster, but now you're using 4 or 5 servers rather than 4,000 or 5,000 servers. Trust me, that's a lot easier, more easily done. I'm not here to tell you that this is going to be Skynet. In fact, I put some code in to keep it from being Skynet. Pretty much any code I write will keep it from being Skynet. But there is a limit, right? The laws of physics still apply. We just bend them a lot more than people are used to. We give you that much bigger server. If you need more than that, then yeah, you're going to have to still pull out the Mongo, Hadoop, Spark toolbox, but we push that out for you much further into the future typically.
So when users still need to sort out some domain knowledge, need to sort out a little bit of capacity time. You want to help the user a lot.
Well, I got to tell you, your questions are very good, okay? But you're out past the boundary of everybody we're talking about. So when we first came into this market and started talking to folks like you, we said, how much memory do you need? You know the answer we got? 5 terabytes would be great. 10 terabytes would be amazing. So the example I used at the beginning, traumatic brain injury, that's a 10 terabyte problem. We take care of that. You got a 20 terabyte problem? I love it. We'll take care of that. I haven't talked to anybody with a 20 terabyte problem yet. Okay? By the time I'm talking to somebody with a 200 terabyte problem, probably we'll have gotten our software past that, right? Because it's software. This is the other cool thing about software. Hardware is evolving. We all know this. Hardware gets better every couple, 3 years. It gets a lot better, right? It's got a step function going for it. Software improves continuously, right? When you talk about a software scaled server, odds are, we'll keep up, right? I haven't talked to anybody who needs even 20 terabytes yet. I'm hoping to. If there's somebody in the room who's got a 20 terabyte problem, see me in the back. Love to get your card. I got some salespeople who would like to talk to you right now.
I understand. It's highly reasonable. I understand that. But sometimes, a lot of people say that it's called scale up or scale out, or it's called burst, traffic burst.
Yeah, but this is the best of both worlds. If you want scale out, you do scale out on scale up, right? Best of both worlds. Yes, sir.
You said your interconnect was 10 gigabytes?
Yeah, 10 gigabit, yeah.
Gigabit, sorry. Just for reference sake, how does that compare to an InfiniBand?
InfiniBand is typically 40. But InfiniBand does, I hope I'm not in the weeds here. So with InfiniBand, you're usually locked into a solution known as RDMA. The issue with most InfiniBand solutions is the processor doesn't move, right? So you're always fetching memory. If you're always fetching memory, you chew up whatever bandwidth you've got really, really quickly. With the TidalScale solution, we're not always fetching memory. Sometimes we're moving that processor to the memory. Much smaller. We don't chew up the interconnect quite as much. And 40 gig is already out there. 100 gig is coming. Right, but 10 gigabit is a lot less expensive than InfiniBand. Same cables all the data centers use. A lot of the data centers are 10 gig already. All right. I can keep going. Are we out of time? We're out of time. Okay, go for it. You're going to have to buy me a beer, though. You got to buy me a beer after this. Okay.
I'm just curious, in your solution, software can be used in different cloud, AWS and Google Cloud?
No, not yet. Not yet.
Only or on-premise?
Yes, because we're a hypervisor, and Amazon does not allow nested hypervisors at all. But stay tuned. right? We're in IBM's,
It's called bare metal.
well, that's what I'm saying, that's why we're in IBM Cloud. So, one of these days, Amazon may offer bare metal with TidalScale on it.
Cool, thank you.
All right, you're welcome.